Now, if you want to read more about Bayesian inference, you may consult these two textbooks for more information. So before we begin, let me just preface this lecture with a short, let me preface this lecture on why we use Bayesian inference. Well, you see, there are many reasons on why to use Bayesian inference. The first is Bayesian inference works better for small data sets. Now, ordinary estimation methods, which we call frequentist, rely on having many observations to be effective. Bayesian inference, however, circumvents that problem. We shall see how it does so later on. Additionally, frequentist inference relies too much on p-values. Now, what is a p-value? Well, a p-value is simply, assuming that the null hypothesis is true, a p-value is the probability that the alternative hypothesis happens. So usually when we do statistical inference, we have 5% as the cutoff point. However, in reality, there is no theoretical justification on why to use 5%. The 5% value was only a rule of thumb devised by Ronald Fisher because he thought that 1 out of 20 errors in experimentation couldn't have been that bad. Bayesian inference, however, relies on estimating distributions for parameters, for example, the linear regression coefficients, in performing analysis. We shall see how later on too. Now, we begin with preliminaries and probability theory. So when we're doing statistical inference, our main goal is to draw conclusions about the population of objects through experimentation. Now, define the set S as the set of all outcomes of an experiment. This set S is called the experiment sample space. So for example, in a coin toss, our sample space consists of the outcomes head or tails. Additionally, for a sample space S, we call any subset of S an event, which contains some possible outcomes. We say that the event A occurs if the experiment outcome isn't the subset A. Additionally, two events A and B are disjoint if their intersection is the null set. In other words, they are disjoint if they don't share any outcomes. So for example, when we're tossing a coin, only events heads or tails can occur. Now, we call any number of sets A1, A2, etc. pairwise disjoint if for any pair of sets A or AJ, their intersection is the null set. So in other words, these events don't share any outcomes. Now, additionally, we might need to divide a sample space into small non-overlapping pieces. So if a collection of pairwise disjoint events A1, A2, and so on all have the union equal to the sample space, then we call this collection of disjoint events a partition of S. So for example, let's say our sample space is exam scores. And we know that exam scores can only take non-negative values from 0 to infinity. Then the sets AI, comprising the closed interval from I to I plus 1, form such a partition. Now, additionally, we need one final technical definition to overcome some theoretical difficulties which we won't get into. A collection B of subsets of B is called a sigma algebra if it satisfies the three properties. First, the collection B contains the null set as an element. Next, the set A being an element of B implies that the complement of A, or any elements that are not in A, is also an element of B. In other words, we say that the set B is closed under complementation. And last, the existence of these sets, of a number of sets as elements of B, implies that their union is also in B. In other words, the set B is closed under unions. Now, we also have the third property. Now, by the third property of sigma algebras, we also have that the intersection of a number of sets is in B, or B is closed under taking intersections, which is true as we see by the following equation down below. Now, a probability function is a function which associates an event A with a number between 0 and 1 called the probability of A. So given a sample space S and its sigma algebra B, the probability function with the sigma algebra as its domain satisfies the following three properties. First, the probability functions are non-negative. Next, the probability of the sample space is always equal to 1. And last, for pairwise disjoint events A1, A2, and so on, the probability of their unions is equal to the sum of their probabilities. Now, while any function which satisfies the axioms is a probability function, the question of which probability function to use is separate. So later on, we will see this when we discuss normal distributions, binomial distributions, and so on. Now, while legitimate probability functions satisfy the three axioms, it is much too tedious to test all probability functions against them. Instead, however, we can define a probability function using the following theorem. So let S be a finite set of elements S1 to Sn, and let B be any sigma algebra of S. And let P1 to Pn be non-negative numbers with sum to 1, or unity, because many probability theory textbooks use unity to mean 1. So for any A as an element of B, we define P of A as the sum of all non-negative Pi, such that with the condition that the probability of A equals the probability of the null set equals 0. Then we have that P is a probability of the function defined on the sigma algebra. So we prove this by showing that the function P satisfies the three probability function axioms. So axiom 1, since all the numbers are non-negative, we have that for any A as an element of B, the probability of A is equal to the sum of the probabilities and is non-negative, satisfying axiom 1. Next, it is true that if we take the sum of all the numbers Pi, we have that their sum is equal to 1, which is just the probability of the sample space, as axiom 2 states. And last, so let the sets A1 to AK denote pairwise disjoint events. Then, taking the probability of their union leads to this equality. Now, we know that the first and third equalities are true because this is how the function P is defined. Additionally, the second equality is true by hypothesis of disjointedness, satisfying axiom 3. Now, we have another theorem. For a probability function PR and any set A as an element of B, then first, the probability of the null set is 0. Next, the probability of the complement is equal to 1 minus the probability of A. And last, the probability of any event A is less than or equal to 1. So first, we prove property 1 by rewriting the sample space S as the union of the sample space S and the null set. So by the additivity principle, we know that the probability of the union is equal to the sum of the probabilities. And since the probability of S has to be 1, it must be that the probability of the null set equals 0. Next, we also know that the events A and A complement form a partition on S, so that we have that the probability of their union is equal to the sum of their probabilities, which is just 1. So performing some algebra, we can see that the probability of the complement is equal to 1 minus the probability of A. Now last, the probability of A is less than or equal to 1. Well, we have that the probability of A complement is greater than or equal to 0. So by the previous property, we get the result. The next theorem, for probability function PR and sets A and B in the sigma algebra B, we have that the probability of the intersection of B and A complement is equal to the difference between the probability of B and the probability of the intersection of A and B. Next, the probability of the union A union B is equal to the sum of the probabilities of A and B minus the probability of their intersection. And last, A being a subset of B implies that the probability of A is less than or equal to the probability of B. So first, we must note that we can rewrite B as like so. So that we have that by additivity property, the probability of B is equal to the sum of the probabilities of these unions, since B intersection A and B intersection A complement are disjoint. Now we obtain this result simply by rearranging terms. So just subtract the probability of B intersection A from both sides. Next, for this property, we know that the union of A and B is equal to the union of A and the intersection of B and A complement. Since they're disjoint sets, we can rewrite the equation as follows, giving us our result. Now last, we know that A being a subset of B implies that their intersection will just be A. So using our first result, we know that so using the first result, we know that the probability of B intersection A complement will just be equal to the probability of B minus probability of A, which is greater than or equal to 0, satisfying, giving us our result. Now, as a note, the second result of the last theorem gives a usual inequality that the probability of A intersection